Welcome everyone. Today what we're going to do is we're going to do some conversions from grams, which is mass, to moles, from moles to particles, and we're going to introduce also how to convert from moles to volume under STP conditions. So to go from grams to moles, what we're going to do is we're going to use what I call formula number one. Moles can be found by getting the mass, which is expressed in grams, so we'll call it the grams given, okay, which is really the mass, and then you're going to divide that by the molar mass. So if you're going from grams to moles, basically, if you plug that into the formula, when you're going from grams to moles, if you're going this way, you're going to end up dividing by the molar mass. And if you're going backwards, if you want to go from moles back to grams, you're going to end up multiplying by the molar mass. Now, another formula that we have is if we're going, let's say, from moles to particles, there's a second formula. We'll call it formula number 2 over here. We're going to put here that particles like this can be found by multiplying moles by a constant known as Avogadro's number, which is 6.02 times 10 to the 23rd. This number is known as Avogadro's number. I'll write that down here. And what we're going to do here is basically, if you want to solve, if you want to go from moles to particles, so you're going this way, all you do is plug the number in here, and according to the formula, you just simply multiply by Avogadro's number, which is 6.02 times 10 to the 23rd. And if we are going backwards, what we're going to do is we're going to divide by Avogadro's number, again, by 6.02 times 10 to the 23rd. Now, what exactly is a particle? Well, a particle is a generic term. It depends on what type of, what we're talking about. If we're talking about an element, we're going to use the word atom to describe a particle. So anytime it's an element, we'll refer to it as an atom. So an atom is a type of particle, a specific type of particle. If we're looking at a compound, it depends on the compound. If the compound is covalent, then we use the word molecule to describe it. And if the compound is ionic, then we're going to use the word formula unit. So a formula unit, a molecule, or an atom are specific types of particles. Now we do have one more conversion, and that has to do with moles to volume, which is expressed in liters. If you look here, this only works under a condition known as STP conditions. STP stands for, it's an acronym for standard temperature and pressure. And the conversion is that if you have 1 mole of any gas at STP, it occupies 22.4 liters. So when you do use the conversion, if you're going from moles to volume to liters, you're going to basically multiply by 22.4 if you're going in this direction. And if you're going the opposite, if you're going from liters back to moles, you'll end up dividing by 22.4. Now I know that looks a little messy there, so we'll patch this up as we go through each step. So what we're going to do first is we're going to look at every single type of possible problem that you can use, and I want you to think of this as a roadmap. It's a flow chart. Here's our first problem. They want us to find how many moles are in 158.1 grams of, this is lead 2 sulfate. So in the flow chart, we are in grams, and this is really just a one-step problem. We want to go from grams to moles, and if you look at the flow chart, all you got to do is you got to divide by the molar mass. We're going to use that first formula, or formula number 1. And what you need to do here is we need to find the molar mass of lead 2 sulfate. So we'll go ahead and do that. We have 1 lead, 1 sulfur, and 1 oxygen. Okay, and then we're going to go to the periodic table and find their atomic masses. So we got 1, 1, and 4 of these in the formula. Lead is 207.2. Sulfur is 32.06. Some periodic tables you can round it to 32.07. We'll keep it at 32.06. And this is 16. Then we're going to multiply across here. This is 207.2, 32.06, and this will be 64. And then we're going to go ahead and add these numbers up. So the molar mass here is going to be 303.26 grams per mole. So let's go ahead and get the grams that are given, which is a 158.1 grams. We're going to divide it by the molar mass that we just got. So if you look at the flow chart, that's exactly what we're doing. To go from grams to moles, you simply divide by the molar mass. Then you're going to get your calculator. You're going to go 158.1. We're going to go ahead and divide that by 303.26. And then since there are 4 significant figures in the question, we're going to round our answer to 4 significant figures. And we get an answer of 0.5213, and it'll be moles of lead. This will be PB. Let me write that down. PbSO4. So 0.5213 moles will be our answer. All right, now let's take a look at this one. Convert 0.89 moles of calcium chloride to grams. This time we're going backwards. We're in moles, and we want to go back to grams. So if you recall from the flow chart, to go from moles to grams, you're going to multiply by the molar mass. We're going to need to find the molar mass of calcium chloride. So we'll do that down here. There's 2 elements. There's 1 of these, 2 of these. Calcium is 40.08 from the periodic table. Chlorine is 35.45. We're going to go ahead and multiply across here like this. This one becomes 70.9. And then we're going to go ahead and add these. So 40.08 plus 70.9 is 110.98 grams per mole. Now that we have the molar mass, let's go ahead and get the grams that were given, or I'm sorry, the moles that were given in the question. And then it says to multiply by the molar mass, which is 110.98 grams per mole. You'll see that the moles will cancel. And when you multiply these 2 numbers together, and we're going to round this to 2 significant digits, I get 98.77, but we're going to go ahead and round that to 2 significant digits, so our answer ends up being 99, and it'll be grams of calcium chloride, and that will be the answer to this problem. Okay? Now, look at this next one. Determine the number of molecules that are in 1.25 moles of oxygen. So this time, when you see the word molecules, they want to go to particles. So we're going from moles to particles. Okay, a molecule is a type of particle. Okay, and oxygen is a covalent compound. It's a diatomic gas, so it's a molecule. So according to the flow chart, all you need to do is multiply by Avogadro's number to go from moles to molecules. So you get 1.25 moles, okay? And then you're going to multiply by 6.02 times 10 to the 23rd, because that's how many molecules there are per mole. So if you just simply multiply 1.25 times Avogadro's, which is 6.02 times 10 to the 23rd, and then we round this to 3 significant figures based on the question, I ended up getting 7.53 after rounding times 10 to the 23rd, and this will be molecules of oxygen, and that will be our final answer. Okay? Now look at this next one. This time we want to know how many moles of barium nitride are there in 4.7 times 10 to the 24 formula units. Again, a formula unit is a type of particle. So we're going from particles, and we're going backwards this time from the previous problem. We're going back to moles. And according to the flow chart, we're going to divide by Avogadro's number. That's how you go backwards here. And the reason it said formula units is because barium nitride is an ionic compound. There's a metal and a non-metal there. So according to the flow chart, we're going to get our given, which is the formula units. And all we got to do is just divide by 6.02 times 10 to the 23rd. And this is going to convert it into moles. So let's go 4.7 times 10 to the 24. We're going to go ahead and divide that by 6.02 times 10 to the 23rd. We're going to round to only 2 significant digits for this one. And you're going to end up getting 7.8 moles of barium nitride. Okay, and that'll be the answer to this problem with 2 significant figures. Now we're going to look at something a little bit more complicated. These are what we call two-step problems. They want to know how many formula units are in 5.1 grams of titanium oxide. And if you look here, this is actually titanium 4 oxide. You're going to notice that we're going to need to go from grams to moles first, okay? And then we're going to go from moles to particles. So this is a two-step problem. So to go from grams to moles, we got to get the grams given and divided by the molar mass of TiO2. So we're going to have to go ahead and find what that is. There's 1 titanium and there's 2 oxygens. Titanium has a molar mass of 47.87. Oxygen is 16, so this stays the same over here. This will be 47.87. This will be 32. We're going to need to add these up. So 47.87 plus 32 gives us 79.87. That's the molar mass, grams per mole. So the first step is to go from grams to moles. So we're going to get the grams given, which is 5.1 grams. We're going to divide that by the molar mass, which is 79.87 grams per mole. The G's are going to cancel. We're going to be left with moles. So I got 5.1 divided by 79.87. And I get this number here. I get 0.063853. 762 is the rest. So here, you don't have to round at all, or if you do, make sure we leave a few extra digits because at the end we're going to need to keep only 2. Now, to go from moles to particles, all we do is get this number and we multiply by Avogadro's, and that will take us from moles to particles. So I'm going to multiply by 6.02 times 10 to the 23rd, and I'm going to round my answer to show only 2 significant figures. I ended up getting 3.8. That's to 2 significant figures times 10 to the 22nd. And it's going to be, since these are formula units, okay, I'm going to put here formula units of titanium 4 oxide, or TiO2. And that will be my answer with 2 significant figures. All right, let's take a look at this next one. So this time we're given molecules and we want to find mass. So we're actually going backwards here. We're starting with particles. Remember, a molecule is a type of particle. So we're going to need to convert to moles. So we're going to have to divide by Avogadro's to go from molecules to moles. And then we're going to need to go from moles to mass, which is grams. And if you recall, to go backwards from moles to grams, what we're going to do is we're going to end up multiplying by the molar mass of C2H6. Let's do the first step here. So we're starting with molecules, 6.45 times 10 to the 24 molecules. If we divide by Avogadro's, which will be the first step here, divide by 6.02 times 10 to the 23rd. Let's do that here, 6.02 times 10 to the 23rd. Let me fix this up here. And I'll tell you right now what it is. So the given is 6.45 times 10 to the 24 molecules. We're going to divide that by 6.02 times 10 to the 23rd. And I get 10.714 again, there's more numbers here. I'll just round this to a 3. It's 28571. We're only going to need 3 significant digits, so this should be good enough. So that's how many moles, but we still got to go from moles to grams. So if you recall, to go from moles to grams, we got to multiply by the molar mass. Okay, so let's find the molar mass of C2H6. So there's 2 carbons, 6 H's. Carbon is 12.01. Hydrogen, we round it to 1.01. This will be 24.02. This is 6.06 over here. Okay, now we're going to go ahead and we'll add these up. This will be an 8 here, a 0 here, and we got a 10 here. Whoops, sorry about that. This is let me fix that up here. This is a 10 here, okay, and that will become a 3 over here. So it's 30.08 grams per mole. So the answer now to go from moles to grams is you're going to multiply by the molar mass that we just found, which is 30.08 grams per mole. So the moles are going to cancel this time. So we're going to go ahead, multiply 10.7143 times 30.08. We're going to round this to 3 significant figures. And I ended up getting, and I'll write it over here, 322. And this will be grams, since we went to mass, of C2H6. And that will be our answer to this problem. All right, now we're going to learn how to go from moles to volume at STP. Okay, so here we're given moles, okay, and we want to find volume. So according to this, since it's at STP, we know that 1 mole occupies 22.4 liters. That's our conversion factor. So when we set it up, all we got to do to go from moles to volume is you multiply by 22.4. So if you have 0.37 moles, okay, and here's the conversion factor, there's 22.4 liters for every 1 mole. Essentially what you're doing is you're just multiplying by 22.4. So 0.37 times 22.4, we'll round it to 2 significant digits, will give us 8.3, and the units will be liters of nitrogen gas. And that's it. That's how you go from moles to volume. If we're going backwards, notice here we have a canister. They give you the volume. So the volume here is 69.4 liters. And we want to go backwards. We want to go back to moles, as you can see here. Again, the key word is that it's at STP. So when you're going backwards, you're going to end up dividing by 22.4. Again, you're going to use the conversion factor. So you got 69.4 liters. This time, they're in 1 mole. We know that there are 22.4 liters. But if you look at the math, basically what we're doing here is we're dividing by 22.4 like it says in the flow chart. So 69.4, then we divide by 22.4, and we round that to 3 significant figures. We're going to end up getting 3.10, and it'll be moles of oxygen gas. That will be our answer. But what you're going to see now is that we can also do 2-step problems. Okay? Look at this one here. We're being asked to go from grams to volume, and it does say at STP. So if you look at the flow chart, we're starting with grams. We're going to need to go to moles. So we're going to divide by the molar mass of Cl2, and then we're going to go to volume. It is at STP, so we'll end up multiplying by 22.4. But first, we're going to have to divide by the molar mass of chlorine. Now, chlorine there's 2 of them. Each chlorine is 35.45. So when you do the math, it's 70.9 grams per mole. That will be the molar mass of chlorine. So in the first step, when we convert 46.8 grams and we divide it by 70.9 grams per mole to convert from mass to moles, we're going to go 46.8 Okay, divide that by 70.9, and we're going to get 0.66008. There's more numbers behind that. I don't think we're going to need that. So we're now in moles. And then the next step is to go from moles to volume. You simply multiply by 22.4. There's 22.4 liters in 1 mole, which basically just means multiply by 22.4. So when we do that and we multiply, and we're going to round this to 3 significant figures, we get an answer. We'll write it up here. It is 14.8, and it'll be liters of chlorine gas at STP. So this was a 2-step problem. Now look at this one. This one is similar to the previous one. However, we're starting off on volume. You could tell because it's in units. And we want to go to mass. So we first have to go to moles. And the first thing we're going to have to do is we're going to have to divide by 22.4 because it does say it's at STP. And then to go from moles to mass, which is grams, we're going to need to find the molar mass of helium, and then we're going to multiply by the molar mass of helium. So first, let's start with volume. We got 5.6 liters. According to the flow chart, we're going to divide by 22.4. You see, for every 1 mole at STP, there's 22.4 liters. And essentially, if you look at how I set this up, we're going to just do exactly what the flow chart says, which is divide by 22.4. We're going to get exactly 0.25 moles of helium here. But we're not done. We got to go from moles to grams. Well, when you look at the periodic table, the molar mass of helium is 4.00, and it's grams per mole. So according to the flow chart, all we got to do is multiply by the molar mass of helium, which will cause the moles to cancel. So when you multiply 0.25 times 4, you get 1 to show 2 significant figures. We're going to put 1.0, and it'll be grams of helium. So this was another 2-step problem, from volume to moles and from moles to grams. Now let's take a look at this one. It says, how many molecules are there in 12 liters of carbon dioxide at STP? So this time, if you look, we're starting with volume. And they want us to go to molecules. So we're going to have to go to moles first, and then to particles, which is molecules. So if you look at the flow chart, the first thing we'll do is, it is at STP, so we're going to go ahead and divide by 22.4. Okay, and then to go from moles to molecules, we'll multiply by Avogadro's number. So we'll do that as the second step. So we're starting with 12 liters. And we know that in 1 mole, there's 22.4 liters. So as you can see in the flow chart, it says we're going to divide by 22.4. So let's do that first. So when we divide, we get 0.53574 and change. There's more numbers there. That's plenty. We're only going to need 2 significant figures. So we just converted it into moles. The second step in the flow chart says to multiply by Avogadro's number, and that will convert us to molecules. So when I multiply by 6.02 times 10 to the 23rd, I'm going to go ahead and round it to 2 significant figures, and I end up getting 3.2 times 10 to the 23rd, and it's going to be molecules of CO2. Notice we don't even need to find molar mass because grams is not involved in this problem. So it's 3.2 times 10 to the 23rd molecules of CO2. All right, we got one more. Here we want to know, what would the volume be of 2.3 times 23rd molecules of carbon monoxide at STP? Okay, so we're starting in particles. Okay, so a molecule is a type of particle. As you know, we're going backwards here, so we're going to need to go to moles using our flow chart. And in order to do that, we first divide by Avogadro's, which is 6.02 times 10 to the 23rd. And then we're going to go from moles to volume. And notice it says STP. That's the key word. That lets you know that we're using the 22.4 liter conversion factor. We're going to end up multiplying. So let's do the first step. We're starting in molecules, 2.3 times 10 to the 23rd, according to the flow chart. To go from molecules to moles, we divide by Avogadro's, which is 6.02 times 10 to the 23rd. So let's go ahead and do that. So 2.3 times 10 to the 23rd, divide that by 6.02 times 10 to the 23rd, and we are now at 0.38206. I rounded it. We only need two significant figures, so this will be now moles. But we got one more step. So in the next step, we want to go from moles to volume. So if you recall, there are 22.4 liters for every 1 mole. Okay, so we're going to go ahead and multiply, which is what it says in the flow chart. And when you do that, and we round to only two significant figures, we're going to end up getting 8.6. Okay, and the units for volume are going to be liters of carbon monoxide, and that will be our final answer in liters. Okay, so you'll notice that we had several two-step problems. You can have a problem, we did one going from grams to moles, and if you recall, if you're going from grams to moles, you simply divide by the molar mass, okay? And then we saw a problem when we were going from moles back to grams, so you multiply by the molar mass. Okay, then we also saw from moles to particles. So if you're going from moles to particles, again, a particle could be an atom, a molecule, or a formula unit. You simply multiply by Avogadro's, which is a constant. It's 6.02 times 10 to the 23rd. If you're going backwards from particles back to moles, then you're going to end up dividing by Avogadro's, again, by 6.02 times 10 to the 24. Now, if it's at STP, which in these problems are going to be at STP, we know that under STP conditions, if you're going from moles to liters, you simply multiply by 22.4. And if you're going backwards, if you're going from liters back to moles, you're going to divide by 22.4, and that's based on using the conversion factor when it's at STP. We also saw that a problem can be a two-step problem. We saw a problem that can go across like this. Okay, we then saw a problem going from particles back to grams. So we did get to see that. Okay, we also saw problems where we're going from grams to volume or from volume back to mass. Okay, and we did also see a two-step problem where we're going from volume to particles or from particles back to volume. So we got to see pretty much all the different types of problems, whether it be a one-step or a two-step problem. But this flow chart should be very useful. It should be a roadmap to help guide you how to go from one step to the other.